Alrighty, so yeah, let's get to it. I figure we might as well start with these questions, right? And then we can always add as we see fit. All right, so let's start off with page 345, number 6. Okay, so 2-point particles with charges Q1 and Q2 are located or separated by a distance L as shown in the figure. So I'll draw out the figure here. So it looks like I have x-axis and y-axis. And the two charges are Q1 is up here and Q2 is down at the origin. Okay. They are separated by a distance L between them. And if we look at, we're interested in a point A here, and that point A is a distance L over 4. Okay. The electric field at that point, at point A, is 0. Okay. So the electric field here at point A is 0. Okay. And our goal here is to determine what the ratio, so find the ratio of Q1 to Q2. Okay, that's our main goal for this question. All right. Okay, so in order for the electric field to be 0 at that point, we need something to happen, right? So if I zoom in here, we essentially need the two electric field vectors to cancel each other out. Okay, so the electric field, let's assume, essentially we have to assume that they're either both positive or they're both negative. Okay, so if I assume they're both positive, then the electric field from Q1 will extend downwards like this, right? So this would be E1. And the electric field from Q2 will extend away from Q2, so it'll extend up like this. So E2 will extend upwards, okay? And they're extending from point A, right? Because I'm interested in what's happening at exactly point A, okay? And so let's write down the, let's write down the electric field due to each of these 2-point charges, okay? So E1 is given by K Q1 over R1 squared, okay? Now, R1 is the distance separating Q1 from the point A, okay? So in this case, R1 is equal to L over 4, all right? So coming back to my equation here, I get E1 is equal to K Q1 over R1 squared, which is L over 4 squared. Okay. And I can do just a little bit of simplification here, right? I can expand out the bracket in the denominator here, right? So I can make that look a little bit nicer. So I get K Q1 over L squared over 16. And if I, right now this is kind of messy because I have a fraction within a fraction. And so what I'm going to do is I'm going to flip the 16 up to the numerator, okay, just to remove that fraction within a fraction. So E1 is equal to 16K Q1 over L squared. Okay. Okay, so now let's do the exact same operation, but going back to my picture here, let's develop a formula for E2, right? Our electric field due to the second point charge, all right? So the setup is the exact same, okay? So E2 is equal to K Q2 over R2 squared, okay? Coming back to the picture, though, we notice that R2 is the distance between the point charge Q2 and the point A. So this is R2, all right? Now to find R2, I notice that R1 is equal to L over 4, which means that R2 would be equal to 3L over 4 because the entire distance between the two charges is equal to L, right? So if there's L over 4 between Q1 and A, then there has to be 3L over 4 between A and Q2. Okay, so that gives me my R2 value. So coming back over here, I'll have KQ2 over 3L over 4 all squared. And again, I'm going to expand out my denominator here. KQ2 over 9L squared over 16. Okay. And then again, I'm going to just clean up my messy denominator there. So I get 16KQ2 over 9L squared. All right. And so now what I have, or what I've developed here, is I have two equations, one for E1 and one for E2. All right. Now in the question, I am told that the electric field at the point A has to be equal to 0, right? And what that tells me is that these two electric field vectors are the exact same magnitude, they just point in opposite directions, right? So to finish off this question, what I'm going to do is I'm going to set these two equal to each other, right? Since E equals 0 at the point A, we know that the magnitude of E1 has to be equal to the magnitude of E2, okay? So what that tells us is 16KQ1 over L squared equals 16KQ2 over 9L squared. All right. And what I notice here is I have some things that are the same for both, right? So I have an L squared and an L squared in both of them. I have a 16K and a 16K in both of them. And so what I'm going to do here is I'm actually going to cancel some things out. 16K is gone, 16K is gone, L squared is gone, L squared is gone. And what I'm left with is Q1 equals Q2 over 9. Okay, or another way of writing this is Q1 divided by Q2 equals 1 over 9. Okay, so the ratio between Q1 and Q2 is 1 coulomb to 9 coulombs. Okay, and that would be my answer for Q1 to Q2. So the way I can write this is Q1 Q2 is the same thing as 1 to 9. And that would be my ratio. How was that? Was that okay? So 6 is done. All right, are we ready for 7? Okay. Okay, so I'm going to do a quick sketch here. It's awful. Let's move this so it's centered. There we go. Okay, now I'm going to just erase the Okay, so I have, in this question, I have 5 point charges, and they are all equal, and they are spread around a semicircle, like so. Q2, Q, or just Q, Q, Q up here, and one last Q. Okay. So each of these point charges has a charge of 7.5 coulombs. And the radius of this semicircle is 2.3 meters. Okay, actually I'm just going to call that R, and R is equal to 2.3 meters. Okay, what we are interested in is the electric field at the origin. Okay, so we want to figure out what the electric field at the origin is. Okay, that's our goal for this question. Okay, so to figure this out, now there's a question earlier on in this section, right? Question 4 on the same page here. What it tells you to do, it gives you a hint of applying some sort of symmetry to this problem. Okay. Now, the first thing we're going to do here is actually the same idea. We want to apply some symmetry to this problem, okay? Just to see if it becomes a little bit easier for us to manage, okay? And that's oftentimes what you want to try to do when you're dealing with some sort of distribution of charge like this, is to consider some sort of symmetry to try to make the problem easier on yourself to understand, or to make the calculations a little bit more manageable, right? And so what I'm going to do is I'm actually going to label each of these charges, right? So I'm going to go around the circle. I'm going to call this Q1, 2, 3, 4, and 5. Okay? Now what I'm going to do is I'm going to pair these up. I'm going to consider first what's going to happen with Q1 and Q5. All right? I'm going to ignore all the other charges. I'm just going to look at what's happening with Q1 and with Q5. Okay? And I'm going to draw kind of a separate picture about what's happening with those two. Okay, so I'm gonna pop these out a little bit. So steps: first, consider Q1 and Q5. Okay, so I have Q1 here. I have Q5 right here. I have my origin right in the middle. Okay. Now, since Q1 and Q5 are both positive point charges, the electric field will point away from each of them, right? So Q1 will generate an electric field, and Q5 will also generate its own electric field. Now, because they're both positive point charges, the electric fields will be pointing... So if I look at the electric field first from Q1, the electric field actually points to the right? So this would be E1. Okay. And because Q5 is the same point charge, the same positive point charge, it would point to the left. This would be E5. Okay. However, there's kind of a crucial bit of information here. Okay. Since both of these charges, because they're spaced around the semicircle, when we come back up to here, they're spaced around the semicircle, and the radius of that semicircle is always r, right? What that tells us is that both Q1 and Q5, they are both a distance of r away from the origin, right? They're both equal distant away from the origin, okay? Now, if we write down the formulas for the electric fields, the two electric fields that we're dealing with here, E1 equals KQ1 over the distance between the charge and the origin, right? So that's R squared. And if I write down the electric field from the fifth point charge, E5, is equal to KQ5 over the same distance, r squared, because they're both r away from the point that we're looking at. They're both r away from the origin. Then what I end up seeing here is, since I'm told in the question that both Q's have the exact same charge of 7.5 coulombs, when I come back to these two formulas here, I notice that E1 is K times 7.5 coulombs over r squared, and E5 is equal to K times 7.5 coulombs over r squared. Okay. So J what this tells us is that because we kind of considered symmetry, Q1 and Q5 in this picture here, Q1 and Q5, it doesn't even matter that they're there, right? The electric fields that they're both generating will just cancel each other out. So it's almost like we can just remove these 2 point charges, right? These 2 point charges don't even influence the problem anymore, okay? Okay. So now let's keep going up the circle, right? Let's switch our attention to Q2 and Q4, okay? So next, okay, but same idea. So I'm going to draw out the picture again. So Q2 is somewhere up around the circle here. Q4 is also up around the circle. The origin is somewhere down here in the middle, right? So there's my origin. Both of them are a distance of r away from the origin. Okay. All right. But this time we have to be a little bit careful. We still assume that they're both positive charges, right? They're both the same charge. So when we plot the electric field, so the electric field from Q2 will point down in this direction, right? So this is going to be E2. And the electric field from Q4 will point in this direction. So this will be E4. All right. Now in this scenario, right, it should be obvious that the electric fields are not going to perfectly cancel out, right? So we saw a perfect cancellation between E1 and E5, but we're not going to get a cancellation here, right? These two vectors do not add to give us 0, okay? However, they will cancel in the x direction, exactly. Yes, exactly. So this is where we have to consider components, right? If I break these two vectors up into components, I have E4x, and I have, E4y, and I have E4x. Okay. And then if I look at this vector, I have E2x, and I have E2y. Okay. And so, yeah, just like you said, Costa, I immediately recognize, oh, look at E4x and look at E2x, right? For the same reason as why these two vectors canceled each other out, right? E1 and E5 in our previous step, we notice immediately that E2x and E4x will also cancel each other out, right? So what that tells us is that there's no electric field, or there's no net electric field in the x direction. The x direction just cancels itself out, okay? We are only left with E4y and E2y, okay? And so right now our job has to be to figure out what E4y and E2y are, okay? Okay, so going back up to my main picture here, one thing I have to recognize, because these are evenly spaced around the semicircle, the angle between Q2 and the angle between formed by Q2 and the origin, this is going to be 45 degrees. Okay? And that's going to become important because we're actually going to have to break down the vector into its components. Okay? So coming back down to our picture with Q2 and Q4, this here will be 45 degrees, and this here will be 45 degrees. Okay? Okay, so now let's actually write down some expressions for E2y and E4y. Okay, so first, E2y is going to be equal to E2 times cosine of 45. Okay, and E4y is going to be equal to E4 also times cosine of 45. Okay. And so I can actually plug in my formula for E2 and E4, right? So E2 is K Q2 over R squared times cos 45. And E4y is equal to K Q4 over R squared times cosine 45. Okay? But I know the values of all of these things, so now I can just plug them in, right? So K is 9 times 10 to the 9. Q2 is 7.5 coulombs. R squared is 2.3, so 2.3 squared. Cosine of 45. And I do the exact same thing with E4y, right? But because the charges are the same, these two quantities just end up being exactly the same, which is nice, right? Let me move this over a little bit. Okay, and so then I can evaluate each of these separately. So calculator, 9 times 7.5 over 2.3 squared times cos 45. That's a really big electric field. 9,022,000. Oh wait, no, 9,022,629,060 Newton per coulomb. Okay, and because the two charges are exactly the same, I'm going to get the exact same value again. 9,022,629,060 Newton per coulomb. Okay. Wait, what did you round though? Okay, one Okay, so I'm getting there, right? So I have E2y and E4y now. Okay, now if I go back to this picture, what's going to end up happening if I kind of just redraw my picture here, because E2y and E4y are both pointing in the same direction, they're just going to add up together. So I get E2y plus E4y in the negative y direction. Okay, so what I can do here is I can add both of these up. E2y plus E4y equals, and I just take the value that I had, and I get 1.8 4525812 times 10 to the 10 Newton per Coulomb. Okay, so I'm getting there now, right? So if I go back to my my main picture up here, right, my main semicircle picture, it looks as though I have dealt with I've dealt with Q1 and Q5, right? I noticed that those just canceled each other out, so I don't even have to consider those anymore. I have done Q2 and Q4, and I've figured out that some of it cancels out, right? The X components will cancel out, but the Y components just add up together, okay? So all I'm left here with is Q3. So my only job now is to figure out the electric field generated by the third point charge in my circle, okay? Now, because this one isn't part of a pair, it's just by itself, I don't really have to do too much extra work here. I'm just going to consider Q3 kind of by itself, all right? And so, last but not least, my next step, my last step, is, so lastly, consider Q3. Okay, so if I look at Q3 is here. My origin is down here. Whoops. And so the electric field generated by Q3 will point in the negative y direction, right? Because again, we're assuming all the point charges are positive, right? And so here will be E3, all right? And because there's nothing balancing this out, it will just be E3. There's no cancellation. There's nothing like that, okay? And so let's calculate what E3 is. So I know the distance between the point charge and the origin. That is R, all right? And so E3 is equal to K Q3 over R squared. So that's 9 times 10 to the 9 times Q3, which is equal to, what was it, 7.5 over 2.3 squared. Okay, and that's going to be equal to Newton per Coulomb. So about 1.27 times 10 to the 10 Newton per Coulomb. Okay. So now I'm very, very, very nearly done. What I have to do for my very last step is just bring everything together. So I've calculated everything I need to calculate. I just have to merge everything. Okay, so final step. We need to calculate the total electric field. Okay. Now to do that, all I do, because it's vector quantity, I'm just doing vector addition, right? The total electric field is equal to E1 plus E2 plus E3 plus E4 plus E5, right? However, throughout this process, I've done some simplification already, right? So the first thing I notice is that E1 and E5, those are equal but opposite. So those are just going to cancel each other out, right? Furthermore, E2 and E4, the X components will cancel each other out. So I only have a Y component, right? And lastly, E3 didn't have anything to cancel out. It just points in the Y direction. So really, I should update this equation. I should say, when I actually simplify this, it'll be E2Y plus E3 plus E4Y. Okay. And so I actually already added these two together, right? I added E2 and E4Y together already. And so I'm just going to take this quantity and this quantity and add them up. Okay, so let's take this one. Add to that this one. Okay, and when I do that, I get a value of 3.0805 times 10 to the 10 Newton per Coulomb, or approximately 3.1 times 10 to the 10 Newton per Coulomb. And that's that. There is my answer. Okay. Alrighty. Oh, something completely different. Okay, very well, very well. We're into magnetism now. Okay, so a particle carries a charge of 4 times 10 to the negative 9 coulombs. Okay, when it moves with a velocity, so the velocity is 3 times 10 to the 3 meters per second. And the direction it travels in is east, 45 degrees north. A uniform magnetic field exerts a force directly upwards. So the Fm experienced by this particle, we don't know, or do we know what it is? Doesn't seem like we actually know what it is. We just know it points upward. Okay, so we don't know the magnitude. We just know the direction of the magnetic force. Okay. When the particle moves, so we'll call this like VA, and then we have a totally separate problem, VB. If the particle is moving with a velocity of 2 times 10 to the 4 meter per second, and the direction there is upward, there's a force of 4. Oh yeah, interesting. Okay. I kind of see that now. Yeah, yeah. Although it does help you find the direction, I think, right? That's its entire purpose here, is to figure out the direction of the magnetic field, or to help you visualize the direction of the magnetic field. I think, but we'll get to that. The force No, we're looking for the direction of the magnetic field. Well, the first one we're told the direction of the magnetic force, but not the field. Yeah. Okay. Okay. So yeah, in this second scenario, we have a force exerted west on the particle. Okay. So we have to figure out two things. We have to figure out the magnitude and direction of the magnetic field. So Costa, as you said, it turns out that the initial velocity that's given to us, or the initial speed that's given to us, doesn't actually help us at all, right? It doesn't help us solve this problem because we don't know what the magnetic force is, okay? This will help us describe what direction the magnetic field is going in, but it doesn't really actually help us calculate anything, as we'll see in a second. So here we're looking for our magnetic field, right? We don't know what it is. We need both the magnitude and direction of it, okay? So what we're going to do first, let's start with this set of givens, okay? So VB and FM, and I also know what the charge is, right? The charge is 4 times 10 to the negative 9 coulombs, okay? So let's go with this set of givens, and let's actually use this to figure out what the magnitude of the magnetic field is. So step 1, calculate the magnetic field strength. Okay. So to do that, I'm going to use my FM formula, right? FM equals QVB sine theta. Okay. Oh, wait. I need to know an angle. So I think that's where this other part kind of comes in, this east 45 degrees north, right? Because I know everything in this equation, right? So I'm first going to rearrange this, and we're just going to start plugging things in, but we're going to notice an issue here. So I have B, so I want to isolate this equation for B. B is equal to FM over QV sine theta. Okay. So looking at my givens here, right? I notice that I have my charge, I have the speed that the particle is moving at, and I have the magnetic force. Yep. Yes. Okay, let's visualize that, right? So, yeah, thanks, Costa. So if I look at this, I notice I already know what FM, what Q, and what V is, right? So I don't have to worry about those, but I'm missing a value for theta, right? I don't have a value for what the angle between my my velocity vector and my magnetic field is, and that's problematic, right? So as you said, Costa, now what I have to do is use the right hand rule, okay? So we have to be a little bit careful here because our right hand rule is a bit out of order, okay? So okay, prepare yourselves. So to my right is going to be east, to my left is going to be west, up is up, down is down, right in front of me is north, okay? So I'm told that my velocity vector is upward, okay? So my thumb points up, all right? Based on this set of criteria here, right? I know my velocity is upward, so my thumb is up, and my magnetic force, that's my middle finger, points towards the west, so it points to my left, right? So my velocity vector is up, my magnetic force is my middle finger, that points to the left, which means my magnetic field, that's my pointer finger, that points directly in front of me, which is my north direction, okay? So based on the right hand rule, I know that the magnetic field points towards the north. Okay, is that clear for everyone? I know Costa, you got that right. Everyone else is everyone else cool with how we're applying the right hand rule there? By Okay, so let's actually plug in here. Because we know what direction the magnetic field is going to point in now, right? The magnetic field is going to point in some direction towards the north. Okay, and so let's plug in and solve, right? So Fm is 4 times 10 to the negative 5 over Q, which is 4 times 10 to the negative 9. V is 2 times 10 to the 4, sine of 90 degrees. All right, so let's plug in and solve. I get 0.5 Tesla. Cool. Let me just check. I think that's good. But let me just make sure. Page 404. Yep, 0.5 T. Yeah, therefore B 0.5 T north. Yeah. So here, let me switch back to Hangouts. Okay, so here it says that a velocity selector is a device that can essentially choose the velocity of a charged particle. So there's two. Oh, perfect. Okay. So there's kind of two things going on here. I just try to pinch and zoom my book. I'm so used to pinching and zooming the iPad. So, man, technology, man. So I'm going to draw out the little portion of the picture that's actually kind of important here, okay? So, again, I won't fill in all the details here because this is your assignment question, but we'll at least get a good intuition behind what's going on here. So we have the velocity of the particle is to the right? So there's our velocity vector. We are told that the magnetic field points into the page. Okay, and it's a uniform magnetic field everywhere. Okay. Alrighty. And we're also told, so because this is some sort of parallel plate capacitor, right? So we have, say, positive charges up here, negative charges down here. In this region of space, we have a electric field, a uniform electric field everywhere within that parallel plate portion of this experimental setup. Okay. So let's consider what's going on here. All right. So we have two forces at play, right? We have a electric field and we have a magnetic field. And both of those fields will exert a force on this charged particle, right? Are we told... It's protons, right? So it is a positively charged particle, proton. Okay. So in this question, we are told that essentially we want to find a way to get only protons that are traveling at a certain speed to leave this parallel plate capacitor system, right? Now, the proton will feel a force, right? It will experience a force of attraction in the downward direction. So if I kind of imagine that the proton is here and I break this off down here, it's going to feel two forces, right? The first force that it'll feel is due to the electric field, right? So the electric field is going to exert a force downward on the particle. So Fe will be downward, okay? Now, it will also experience another force due to the magnetic field. And now, to figure out what force it'll feel due to the magnetic field, we have to use the right-hand rule, right? So in this case, the velocity is to the right. So that means our thumb points to the right. Our magnetic field points into the page. So our pointer finger is into the page, which means that the force exerted on the particle is upward, right? And so we are going to have a counteracting force, Fm, which points directly upward, okay? Now, the whole purpose of this experimental setup is, and it says so in the question, we want to make the particles travel perfectly straight through the parallel plates, okay? So the electric force wants it to curve downward, right? And the magnetic force wants it to curve upward. Our goal is to make it so that these two forces here are perfectly balanced with each other. They point in opposite directions, but they're perfectly balanced out by each other, okay? So the whole setup with this question is we want Fm, or the magnitude of Fm, to equal the magnitude of the electric force. Okay? And so, we know the magnetic field strength. We know the speed that it travels. We need to figure out what the electric field is that we need. Okay? So, just kind of filling in one more step here, and then I'll let you guys take it from there. We know that QVB sine theta is equal to the magnitude of the electric force, which is QE, right? Now, the only thing we don't know in this equation, we have information about everything in this question except for what the electric field is. So this will allow us to figure out what the electric field is. Okay. Yeah. And that's about it for the setup of that question. Jana, is that a bit more clear? Okay, page 396. Question 5. All right, so we have a current loop that forms a right-angled triangle. So let me draw this out. I'll use the same colors that they use in their... Is it a bad one? Interesting. Okay, let's see if we get that. Okay, so we have our, we're told that the length of this current loop is L. We know that there is a current I flowing through this loop. We are also told that we have an angle theta within this loop that's equal to 39 degrees. Okay. What else are we told? Oh, we're actually given values for this. So L is equal to 1.2 meters. Theta, as I mentioned, 39 degrees. The magnetic field, so the magnetic field are these orange lines here. The magnetic field has a value of, or has a strength of 1.6 Tesla. Okay. And I think that's all we're told, right? Do we know what I is? I guess we don't know what I is. I don't think we need to know what I is. Oh, in terms of theta, L, and then... Okay, yeah, I see. Gotcha. Okay. Yeah. Cool. Okay. So first step first, the part A is actually super easy. Okay. So actually, I'm going to write down the... So we're interested in the force on portions of this wire, right? So the force formula, the force on a wire, is given by F wire is equal to ILB sine theta. Okay. And theta in this case, theta is the angle between the wire, right? Wire and magnetic field. Okay. And so for part A, we are looking at the portion of the wire that is parallel to the magnetic field. So we are looking at this portion of the wire. Actually, let's label these segments. Let's call this segment 1, segment 2, and segment 3. Okay? Now, because segment 1 is pointed parallel to the wire, the angle between segment 1 and segment 1 and the magnetic field is just equal to 0, right? So F wire equals ILB sine 0. But because sine of 0 is 0, this whole thing is just 0. All right, so essentially if a wire is traveling, or if a wire is running parallel to the magnetic field, the force exerted on it is just 0. Okay? Okay. For part B, we have to figure out what the sum of the forces on the remaining 2 segments of the loop are, okay? So again, what I'm going to do is I'm going to consider each portion separately, right? So I'm going to consider portion 2 separate from portion 3, and I'll do those individually, okay? So portion 2, I know that if I analyze this picture here, I notice that the current flowing through portion 2 and the magnetic field, they're perpendicular to each other. So the angle between those two are 90 degrees. Okay? So for portion 2, theta equals 90 degrees. Okay? Because the angle between them is 90. And so I can calculate the force exerted on this wire. F wire equals ILB sine of 90 degrees now. And so this is just 1. Okay? And that tells me that F wire is just equal to ILB. Okay. Okay, cool. We also should note the direction associated with this, right? So if I look at the wire, if I go back to this, right, the current is pointing straight down. So my V is straight down in this case. The magnetic field points to the right in this picture, which means my magnetic force on the wire is coming out of the page back towards me. Okay, so the magnetic force is coming out of the page on wire 2. Okay. Okay, now let's do the exact same calculation, but for segment 3. Okay. So in segment 3, the angle between the current flowing through the wire and the magnetic field is equal to theta, so 39 degrees, right? Theta equals 39 degrees. Okay. So F wire equals ILB sine 39. Okay. Which we can't really do anything with, right? We just have to leave ILB sine 39. Okay. Oh, but we don't. Oh, wait, hold on. I'm making a mistake here, or not a mistake. I have to be super careful. I didn't even notice. I've messed up all my length calculations here. Okay, because if I look back at this picture, actually, let me pop this out a little bit here. I should have named these something specific here. I should have called this L2 and L3, because if I come back to my picture here, what I'm going to notice, here, let me fix this picture up. I know that this angle here is 39 degrees. I know that this value here is L, okay? And so to figure out, let's call this, so yeah, this is L, what was it? L2 and L3. So if I want an expression for L2, I have to note that tan of 39 degrees equals L2 over L. Okay, which means that L2 is equal to tan 39 times L. Okay, or rewriting that, L tan 39. Okay, and I can also come up with an expression for L3, right? So I notice that I have the adjacent side and the hypotenuse here. So I know that cosine of 39 degrees is equal to adjacent, so L over L3. Okay, and that tells me that L3 is equal to L over cosine of 39 degrees. Okay. And now I'm going to take both of these and plug them back up into the two formulas that I developed for the force on each wire segment. Okay, so the force on wire 2 is given by I times L2, where L2 is L tan 39 times the magnetic field strength. And the force on wire 3 is equal to I times L3, which is L over cosine 39 times sine 39. Times B times sine 39. Okay. And so I can do a bit of rearranging here. So I have ILB times sine 39 over cosine of 39. But this here is just tan, right? So I have ILB tan 39. Okay, and if I come back to my equation for F wire 2, I get the same exact thing, ILB tan 39. So these are the two formulas that I'm now interested in. Okay. So I found the magnitude of the force on each of these wire segments, okay? But now what I want to do is I actually want to figure out what the direction of the magnetic force is. Wait, did I say magnetic field? I found both of these equations tell me the force that are exerted on each wire segment. But I have to figure out what direction those forces are in, right? So I've already figured out what the force on the second wire is, right? So FM2 comes out of the page. Now, if I look at the third wire segment, again, I have to use my right-hand rule here, right? So my thumb is going to point in the direction of the current. My finger, my pointer finger is going to point in the direction of the magnetic field, which means my middle finger points in the direction of the force, right? So in this case, my middle finger is pointing into the monitor, right? And so that tells me that FM3 is going to be pointing into the monitor. Okay. So noticing what's going on here, it looks like FM2 and FM3, they point in exactly opposite directions, right? FM2 points out of the page, FM3 points into the page, and they have the exact same magnitude. Okay, so what I'm able to conclude about this is that the total magnetic force on this loop of wire is going to be 0. Okay, so I conclude since FM2, or the magnitude of FM2 equals the magnitude of FM3, right? I found that both of those formulas were exactly the same right here, right? ILB tan 39, ILB tan 39. And since FM2 points out of the page, and FM3 points into page, so because they're equal magnitude, opposite directions, the net force is 0. Okay. So that one was definitely a little bit trickier, I would say. Definitely a little bit trickier. Okay, an electron with a... Actually, I absolutely love this question. I think this is a fantastic question. This is a really good test question. Overall, really good test question. Really, really good test question. Overall. An electron with a horizontal speed... So I'm actually going to draw a picture out for this. So I have a positive plate on top and a negative plate on the bottom. And I have an electron that's traveling through these two plates. Okay, so it will be attracted towards, let's draw it better. It will be attracted towards the positive plate as it passes through this region. Okay, so there's my electron. We are told that the initial speed of the electron, so, and I'm going to set up, actually even before writing down my givens, I'm going to set up a reference frame, a coordinate system for this one. Because what we're going to have is we're actually going to have, this is very similar to a projectile motion question where we have an x direction set of calculations and a y direction set of calculations, okay? And so what I'm going to do is I'm going to say, we're going to make, towards the positive plate, we're going to make that our positive direction. And to the right is also going to be a positive quantity, okay? So I have a x direction and a y direction in this example, all right? And so let's write down our givens here. So I initially have a velocity. It says it has a horizontal speed with no vertical component, right? So that means the initial velocity in the x direction is equal to 4 times 10 to the 6 meters per second. Okay. And there is no initial velocity in the y direction. So v1y is equal to 0. Okay. The electric field, or the magnitude of the electric field between the two plates, so extending from the positive plate to the negative plate, is 150 Newton per Coulomb. Okay. And the direction there is down, or in the negative y direction, whatever you prefer. Okay. Actually, yeah, let's do that direction. Negative y direction. Okay. And the plates are 6 centimeters long. Okay, so let's also label that here. We'll call that dx. dx is 6.0 centimeters. Okay, so coming back to our givens table, dx, the actual length of the plates. Yep. So dx is 0.06 meters. Okay. Part A is asking for the vertical component of the electron's final velocity. So we want to know what v2y is when it leaves these plates, okay? And so this is very much like a projectile motion problem, right? What I want to do is I want to use some set of this information to figure out, well, multiple things. But the first thing I want to figure out is how long it takes, right? I want to find time, okay? Well, luckily, I have the speed in the x direction, and I have the distance that it travels in the x direction. So I have everything required to figure out what time is, okay? So first, calculate time. Okay. And so I know that I have v1x is equal to dx over delta t. And I can rearrange this thing to find my time. Okay, so time is equal to dx over v1x. And then I can plug in my values here. So I know dx is 0.06 meters divided by 4 times 10 to the 6 meters per second. And so I get a value of 1.5 times... It wants to know the final speed in the y direction. So the time it takes for the electron to pass through this region is very, very quick. It's 1.5 times 10 to the negative 8 seconds. So it moves through here extremely quickly. Okay. Okay, so now that I have time, what that will allow me to figure out is it'll allow me to figure out what the final y velocity is. Okay, so next, there is going to be one sub-step in here because I don't know what the acceleration is, right? This particle, because it'll feel an attraction towards the positive plate, it will be accelerating towards the positive plate. So I still have to calculate what that will be, but we'll get to that in a second. Okay, so next, calculate the acceleration Okay, no problem. We're pretty much done after this, so this is it. Yeah, okay. Okay, so calculate the acceleration of the electron. Now to do this, it's kind of a two-part question, right? So because the electron is within a electric field, right? We know what the electric field strength is. We know what direction it points in. We can actually figure out the force on the electron within the electric field, right? So we know that the force exerted on the electron is equal to Q times the electric field. Okay, but we also know that force is equal to the mass of the electron times the acceleration that it experiences. Okay, and so what this allows us to do is it actually allows us to figure out what the acceleration of the electron will be. Okay, and so let's plug this in, right? So the acceleration is equal to the charge of the electron times the electric field over the mass of the electron. Okay, so this is 1.60 times 10 to the negative 19 times 150 Newton per Coulomb over mass of the electron, 9.11 something, times 10 to the negative 31. Yep, 9.11 times 10 to the negative 31. And I should be actually a little bit careful in the way that I'm defining this, right? Because I know that the electric field, it points down, right? So really, when I plug it into this formula, I should be plugging it in as a negative number, right? So be really careful about that. Because we're dealing with like a kinematics problem, essentially, we have to remember direction, okay? Furthermore, the charge on the electron is not a positive charge, it's actually a negative charge. So I should remember a negative on the 1.60 times 10 to the 6, right? So just a couple of little things to remember. But then mass is positive, right? Mass is not going to change. Okay, so let's give this a try here. So I get a value for my acceleration of positive 2.63823. 0.026 times 10 to the 13 meter per second squared. So a very large acceleration. Now, because the acceleration is positive, what this tells me is that the direction is up, right? Or in the positive y direction, okay? Which kind of makes sense based on the picture, right? The picture shows the electron curving upwards as it goes, right? So it makes sense that we get a positive value for our acceleration, okay? Okay, now we're almost there. Now we can figure out the final y velocity, right? We know what time is. We know what the acceleration is. We know the initial y speed is 0. So we have everything we need for the final y velocity, okay? So lastly, calculate final y velocity. Okay, so I'm going to use, again, one of my kinematics formulas. V2y is equal to V1y plus A delta t. Okay, I'm going to plug in all the things that I have. V1y is 0, so that's gone. So V2y is equal to A, which I just found, right? That's 2.638 times 10 to the 13 times my time, which is 1.5 times 10 to the negative 8. And so I plug those in, and I find my final y speed. And I get a value of 395,734 meter per second in the positive y direction. Okay. Alrighty. Now for part B just says what is the final velocity of the electron. So I'm not going to go through that. I'm going to leave that for you guys. But basically, we have the x speed, we have the y speed. You use Pythagorean theorem to find the magnitude, and you use tan theta to find the direction. So you guys have now probably done that, 50 times, 100 times by now. So I'm not going to go through that with you guys. But I'm happy, or I'm certainly I'm certain that you'll be able to go through it. All right.